about actual how you run the model. And this afternoon, the practical will be on installing and running the model, compiling, and doing some tests on different type of meshes using triangles or regular grids and all that stuff. Okay, so oh yeah, so je peux sortir du truc là ou parce que j'ai oublié de coller un truc. How do I get out of this? Je peux prendre un PPT ou à la place? Donc au lieu, ça marche pas? Okay, I'll try this one. All right. So essentially, this is what I just said. WaveWatch 3, the model we'll be using here is it's not just a model; it's a framework. In the framework, you can put many different things because there are actually many different options. So each change of these options actually makes a different model, right? And so there are two types of options. One is chosen at the compile time. So before you compile the code, you have to make some choices. And these choices are defined by a small text file, which is called switch. And as you will see, it's part of the bin directory. And that defines the main settings of the model. But then there is a second level of model adjustment, which is essentially to modify some parameters. And that's done through some name lists, which are defined basically when you run the model, when you define the model configuration, and that's done with a program which is called ww3_grid. And as time passes, since the version 2.22, 3.14, and so forth, now 5.12, there are more and more options, and so many more possibilities to do more crazy things. And so this is where actually I wanted to get out of this and show you what was written on the wiki page, because where was it? So there's this foreword here on the wiki page. So I'll just read it for you. So before we get started, just want to make a few important points. First of all, in all processing or modeling activities, there are many choices that you have to do, with everything you do on the data, what kind of value you set on the parameters, and the danger of providing what we're doing this week, use some cases which are ready to run, examples, is that all these choices are more or less forced onto the users as some kind of black box, and the user may think that these are default parameters. So one of the goals of this week is actually to show you that all these buttons, what they do, and try to emphasize the important ones and what they do. But contrary to the Wave model Swan, the philosophy of WaveWatch is that there is no default parameters. All the parameters are in your face when you open the input files, and this is why it takes a long time to set up the model and figure out what they all do. But our approach here is that you shouldn't use a model if you don't know what it's doing. Okay, and so WaveWatch 3 somehow forces you to go through some of this learning process. And so you need to take the driving lesson because you can actually start the car, otherwise you're going to crash on the highway, right? Of course, don't take it literally. Not, your life's not at risk, but yeah, you can get some crazy results. So that can be a little frustrating, and of course, this is why it's not so easy to set up WaveWatch and run it. So we're trying to make it easier, but still, I just want to emphasize there is really no default parameters. So all the choices are yours. And if you do it wrong, then it's you know, too bad for you. Okay, so that's that was my disclaimer, and so now I'll try to educate you a little bit about all these different choices in the modeling. Okay, so this switch file, which is the most important piece of the code, just one line of text, contains all the choices you can make on the different propagation schemes. So you can use a first order, third order, or second order schemes. You can use different way to average the spectrum to avoid what's called the garden sprinkler effect, which is an effect of discretization of the wave spectrum. If you don't do any processing of that, you get some funny flower shape wave height pattern because the energy will tend to propagate in the discrete directions. So away from a point source, you get some flower instead of a continuous field. And this is activated by this UQ or UNO. There's two methods for alleviating the garden sprinkler effect. And you have the very important choice of generation and dissipation parameterization for how the wind makes waves and how the waves are dissipated. I will go into the detail of that a little bit this morning. Essentially, you can choose between ST1, or first you can choose ST0, which is no wind input and no dissipation, just propagation essentially, or you can put nonlinear interactions and just conserve energy. But ST1 corresponds to the WAM cycle 3 from 1988. ST2 is the parameterization by Tolman and Chalikov, which was tuned to numerical model results by Dmitry Chalikov. ST3 is essentially one cycle 4 with least recent updates from ETMWF. So we've actually so that's the main choice. And then if you look in the manual, there's a table with different parameter values that correspond to the different evolution of settings done at ETMWF. You know, it changed things in 2005, then it changed again in 2010. So every few years, they do some adjustment to get some improvement of the wave model. ST4 is essentially what we developed here, which is more or less based on the work by Banner and Morrison, with the very important difference that we started from the swell dissipation and then corrected the other terms. And ST6 is essentially the Babanin et al. Parameterization, which is based on the inputs from Mark Donnellan with some later corrections. So that's for the input and dissipation. An important thing here, and a lot of people were not happy about it, was WaveWatch a long time ago, is that you cannot mix and match. You know, one input goes with one dissipation. You cannot take the input of Tolman Chalikov, for example, with the dissipation of 1 cycle 4. But technically, there's no reason why you couldn't do it. In practice, actually, there's always a balance between the two. And actually, in some of these terms, the input has an effect on the dissipation. Because typically when waves break, the airflow goes over the waves, and the amount of energy pumped into the waves by the wind should actually be a function of the breaking. So the dissipation input actually are very closely connected. Then you can have different choices for what is called the four-wave interactions. And I will explain to you what that is. You can either have no nonlinear interactions at all. You can use a discrete interaction approximation, which is the NL1 choice. NL2, which takes a long time to run, but is very nice for research, is actually an exact computation of the non-interactions. And NL3 is a multiple DIA approximation. And we're still waiting for NL4, which will be in the next version 5.13, coming from the two-scale approximation, Don Rizio and Will Perry. Then you can do different things with the bottom friction. So BT0 is no bottom friction. BT1 is what's called the John swap parameterization, which doesn't really have much physical basis, but it's some coefficient times the orbital velocities. BT4 is based on the roughness, and that includes an effect of change in roughness due to ripple formation on the bottom. So you have more orbital velocity that will generate some ripples that increase roughness and enhance dissipation. Then there's a lot of stuff about ice, and actually now we also have IC4, and I will not talk too much about it because I don't think that many people here are interested in ice. It's going to be another time. There's some shoreline reflection if you activate REF1, and IG1, for example, can be used if you want to compute the second order spectrum correction in the output, and also if you want to have the generation of infragravity waves at the coast. Now there's different choices for interpolation of the forcing. So you can use a constant piecewise wind, or have it interpolating linearly in time, or with a quadratic fit. That would be WNT0, NT1, or NT2. Is there still the NT4 switch? I thought we got rid of it. NT4 too. Yeah. Okay. So yeah, if you want to use the version 4 of the NetDF library, you have to specify NT4 plus some environmental variable, and we'll see that I think this afternoon. For people that do really small domains like a lab test or a beach, there's a special one to allow time steps lower than 1 second. That's yeah. The thing is that the time in wavewatch is counted in integer seconds. So if you actually want to make a time step less than 1 second, you have to do some extra looping. So this is what this does. And all these switches are repeated in the output. So if you run the model, you don't remember what you've done, don't worry. You can always find, if you have an XDF output file, the switch choices will be repeated so you can know where that is. And the idea is to make the model results as traceable as possible. And we're trying to do the same now with the nameless parameters, but it's not yet fully finished. And so some nameless parameters will appear often in an SCF files, but not all of them. And so as a result of these choices, there's actually not two people running wavewatch 3 in the same way. And also there's probably not one switch fits all configuration. So some regions or some applications are probably better with some parameterization than other ones with some other ones. And how to choose them, it's of course not simple. So that's where the experience comes in. And what I will show you now is actually what happened when NCEP changed their parameterization from ST2 to ST4. That was 3 years ago. And that's so that's the bias against model altimeters. These figures actually are from Harun Chawla. I think it's used JSON, probably JSON 2. So so here the arrows was actually pretty big in the Southern Ocean. Essentially what happened is that Hendrik had tuned the model back in 2000, and they kept the same tuning for 12, 13 years without changing anything. And that's with the new parameterization, that's just the bias. So you actually get a low bias of the East Coast, which we are working on. But overall, it's less big in everywhere. That's the maps with the, okay, so the different curves are, yes, NVSAT, JSON 1 and JSON 2 as a function of months of the year. That's for the year 20 something. I don't remember what Harun did. So you have the bias, you have the RMS error, and you also have the scatter index. So it's not just the bias has been reduced, but the scatter index also has been reduced by typically 30% in the old and the new parameterization, and the correlation has been increased quite a bit. So you can have sometimes it's good to actually improve parameterizations. This is what I was showing you yesterday, the difference between the old version of the EMWF parameterization. Old means 2005, and our ST4, so the Arduino parameterizations. That's a map of error against the altimeter. So again, it's below 10, it's blue, 10%. And then most of the errors in coastal areas are between 10 and 20% for the wave height. So wave height, of course, is only one parameter, and the issue that we don't have so much data about other parameters. Okay, and to give you an idea of actually going from ST1, ST2, ST3, ST4, so the 4 choices you could do in wavewatch until a couple of years ago. Now there's ST6 on top of it, which should be below that, but if you want to know what ST6 does, you can go to the latest paper by, is it Babanin or Tiger? No, I think it's Tiger et al. In Ocean Modeling, published earlier this year. Basically, it's very close to this one. The errors are a little higher. They're less on at short fetch. It's actually behaving better of the US East Coast. And some people tell me it's better for hurricanes, ST6, but I don't know. So, so yeah, so this is a bias, and this is RMS error. So really, the 1+3 was really pretty good in the off Peru. But apart from that, you can really get better stuff. And you see that Tom and Chaikov actually work pretty well in the trade wind area. And so if you're working on Morocco, maybe ST2 is still not that bad. Okay, so what's happening and why do we have these differences? So all these model results on wave height is of course, wave height is an integration of the spectrum. And the spectrum evolution is a result of a balance between the different source and sink terms in the wave action equation. And for young wind waves, so typically waves that go slower than the wind, so U10 is the usual 10-meter height wind speed. CP is a phase speed at the peak of the spectrum. And so when you have this ratio less than 1, it means that typically the dominant waves are forced by the wind, Okay, that's what I would call young waves. And so in that case, we expect to have a main balance between input and dissipation, and that was basic reasoning for how the ST1 or 1 cycle 3 and 1 cycle 4 parameterization were set up. Actually, I'd prefer to call it a balance between atmospheric source and oceanic sink, because in the cooling perspective, you're actually taking energy and momentum from one model and taking it to the other ocean model, for example. So this plot gives you one possible quasi-balance. It's not exactly balanced because the sum of all the terms, so he has three terms: the input, the nonlinear interactions, and the dissipation. And the sum of all three is a red curve. And this is, okay, you have the units here. This corresponds to starting a uniform ocean with a wind speed constant at 15 meters per second. And that is a state of the ocean after 3 hours. So you have also on top of that the peak of the spectrum in black. So the spectral peak is here, okay? And you see that you have a strong wind input above the peak and all the way to the high frequency. That's the blue line. So here it's integrating directions. I'm just showing the frequency spectrum. The nonlinear interactions are taking energy, so it's negative here, so it's meaning taking energy here and transferring it to both the lower frequencies and the higher frequencies. That's the famous double cascade of energy, which goes to both larger scales and shorter scales. And then the other important term in there is the dissipation term, which is this brown line. The way it is parameterized here is basically based on the idea of flips that it should be a function of what is called the saturation spectrum, or in other words, the non-dimensional spectrum, which is some way to say that it's a function of the steepness of the waves, but that steepness is computed locally in the spectrum. So here, the steepest waves are near the peak, and so this is where you get stronger dissipation. Above the peak, the waves are a little less steep, and so you get less dissipation. Right? So that's basically how it works. And so the sum of the three is this red curve here. And so you see that the red is positive on the forward face of the spectrum at low frequencies and negative here, which means that this part of the spectrum will gain energy. So the peak will shift here and this will go up, and that part will slightly go down. And so if you integrate that up to 48 hours later, you end up with a spectrum which is all the way here. And you can notice that I've changed the scale. So I multiply this by 10 to the minus 3, and this is now 10 minus 4, meaning that the peak here is actually 10 times higher than this one. There's much more energy here. So wave height now is up to something like 6-7 meters. And here it's probably around 1 meter, 1.5 meters. So the peak is much higher, and it's been shifted toward lower frequencies. You can see that we have almost an equilibrium. The red line here is almost zero all the way to high frequencies, because essentially the input is balancing the dissipation at all the frequencies, but we still have a little bit of shift towards lower frequencies, and actually this imbalance of input dissipation is related to the swell and how the wind waves transfer energy to the swell. In this parameterization, there is a negative input, so some energy is lost by the wave going back to the atmosphere, but you can see it's not big enough to compensate for the nonlinear transfer, which is a green line, and so as there's still a net growth of waves as it develops. So this parameterization, tends to have a wind speed that's still growing even after a long time. So that's one example of how things happen physically. So the three source terms. The first one is this wind input. It physically comes from the fact that if the waves go slower than the wind, so imagine the waves here is going from the left to the right, and the wind is going the same direction. In that case, you typically have a higher pressure on this side and lower pressure on that side. It's just a aerodynamic effect over the waves. And when you have that, the pressure on this side is going to push on this side of the waves going down, and on this side it's going to be pulling up. And so as a result, because the pressure is pushing in the same direction as the velocities, we have a network of the force. The pressure force is working on the velocities, providing energy from the atmosphere to the ocean, just computing the work of the forces on the sea surface. You can also get some work if you look at the stress. The if you have a stress which is stronger in the orbital velocity direction here, and then a stress modulation in that direction there, that will also work on the waves. But in general, the modulation of the stress is much smaller than the pressure effect. And now the big question is how we quantify this pressure difference between the two sides of the wave. And so already with monochromatic waves, it's pretty complicated. But especially with real waves that are breaking and everything, it's a big mess. And so there's many people that are working on this and still working on it. So actually, if you want to look at this, it's a very nice paper by Jeffries from 1925, which actually forms the basis of what's probably the most correct approximation of what's happening, especially at high winds. Nicolas Larreul did his PhD on airflow over breaking waves in Marseille some time ago. And that was also taken up by Laurent Grave, who actually was making very nice measurements of pressure and shear stresses all the way to the sea surface. And Mark Donnan did also very nice experiments in situ, showing that typically the pressure difference between the two sides of the wave is a function of the steepness. And you expect that at some point, if the wave is very steep, the airflow will separate, and so you get like a recirculation bubble on the other side, and that makes a big pressure difference. And depending on how strong this separation is, you get much a stronger or weaker wind input. And that is the basis for the ST6 wind input. And that's the only parameterization in wave that has this kind of effect. Now, the school of the theory, so all these guys actually are more experimentalists, actually made measurements of pressure over waves. Then you have the theoreticians that know nothing about the real waves. Starting from Miles and looking at the instability of the waves when you have, and actually that's a general thing also with internal waves in the atmosphere. If waves get at a point where the phase speed equals speed, the mean flow, you have what's called a critical layer. And that singularity in the Rayleigh equation gives you a transfer of energy from the waves to the mean flow. So this is actually how people parameterize the drag of the internal waves in the atmosphere, which is slowing down the atmospheric circulation, which is very important for weather forecasting. And the same thing here for waves. When the waves get to the same speed as the velocity of the wind, there is something special happening at that height, and that is exchanging energy and momentum between the mean flow and the waves. Now, there's been a lot of, so Miles did that with a prescribed wind profile, and then Fabricant modified it to take into account the fact that because the waves take momentum from the wind, then the wind profile should change. So this is called the quasi-linear generation mechanism. And that was taken up again by Peter Janssen and parameterized, and that's the basis of the 1-4 parameterization. One of the interesting features of that parameterization is that it tends to give a stronger wind input for a young wave, which is actually goes a little in the same sense as having a stronger input for a steeper wave, except that in reality, if waves get really very steep at some point, the drag coefficient goes down because the airflow completely separates. So that's yeah, some of the nice feature of this Janssen parameterization. And then there's been a lot of people that have done some numerical modeling with CFD codes of how the airflow evolves over the waves and how you can compute the pressure over the wave. The problem with all these models is how you treat the turbulence and the question of turbulence closure. And there's actually a very nice recent paper, more theoretical than numerical, by Miles 93, looking at what's happening above the waves. At some point, a typical thing people do with boundary layers is you say that the mixing length in your turbulence scheme is a linear function of the height, that's a Prandtl approximation. But that's okay if you don't have any waves. Once you have waves, you have competition between the eddies, which are mixing the air, and the waves, which are shaking the air around. And at some point, and this is very well explained by Miles, you actually go from a viscous type mechanism in which the eddies are making things to an elastic mechanism in which the waves are shaking the air on a time scale that is shorter than the eddy turning around. So if the wave is shaking the air faster than the eddy is turning around, then you don't mix things anymore. And that's the elastic turbulence closure by Miles. And there's a lot of the British guys, Belcher and Hunt, have been working on how the turbulence is distorted by the wave motion. Basically, all this numerical stuff ended up in some ST2 parameterizations by Chalikov, and there's some more work by Kutas and Makin working on this. What all these people actually didn't look at too much, and there's some further paper by Hara and Belcher, is okay, so that's for, imagine we have a monochromatic wave, we can say something about it, but in a wave spectrum, we have long waves and short wave on top of them. And what is actually the effect of the long waves on the short waves? So there's a lot of hand waving argument. And so the Hara and Belcher paper is like that. Well, okay, so the long waves are taking momentum, so the short waves, they actually are sheltered, they don't see the same momentum flux, blah, blah, so you should reduce the U star. And then you can do some cooking recipe, and so that's the win input. So basically, it's a big mess, and in the end, for the same wave spectrum, ST2 gives you input which is 3 times less than ST3. And ST6 can be much bigger, and in the end, we don't really know what is true, because there's very little measurement of that. Okay, now the nonlinear interactions. We have some very nice theory, which of course is based on this assumption of weakly nonlinear waves in homogeneous conditions, looking at the large time limit of the evolution of the spectrum. And that gives you a rate of change of the spectrum at one wave number, call it K4. You will have this crazy integral over all the other spectral components, which gives you how the spectrum changes. And basically what happens is if you have K1 plus K2, which is equal to K3 plus K4, and sigma 1 plus sigma 2 equals sigma 3 plus sigma 4, then this is called the resonance condition. And this corresponds to the type of wave number quadruplet. So you imagine you have 4 wave number interacting, and they will change energy according to this formula. And I didn't write for you this P, but that takes a full page of equations. So it's all in the Hasselmann 62 paper with some errors for shallow water that was corrected later by Hartadich and Hasselmann. And this is included in the WaveWatch code with what's called the NL2, the exact nonlinear interactions of four waves. So the issue in practice, if you want to forecast waves for tomorrow, is that at each point of your grid, each spectra, you have to compute this 3-dimensional integral over all the spectra, and that takes a lot of time. So there's smart ways to do integrals. People have used Gaussian quadrature, people have used some kind of funny Chebyshev polynomial, whatever, but still, on each curve, you end up having at least 20 points, and you have to sum that up and do something. So to avoid that, Susan Hasselmann, the wife of Klaus Hasselmann, this guy here with the hat, that was a picture 10 years ago. So they devised the parameterization, instead of taking all the full integrals, say, okay, we're going to say that normally you can have K1 plus K2 is one vector, and then K3 can go on all the other curves and go around. And they say, okay, we're going to take K1 like this, and K2 like that, and then K3 and K4 will have this geometrical configuration, nothing else. So of course, K1 will turn, and K2 will follow, and then K3 will always be to the left or to the right with 1 point something, 1.3 times K1, but not 2 times or 3 times more. So it would choose a reduced set of the interaction, and that's that. And so the coefficient that goes in front was tuned to reproduce the downshift of the spectrum in growing seas. And that seems to work pretty well. Of course, the shape of the non-interaction function is really bad at high frequencies. The directional distribution is really bad. So there's some very nice papers by Don Rizio about that in particular. But in all practical applications, this is what people are actually using. And now dissipation. So the basic idea of dissipation is that the waves break when they are very steep. And the question is, okay, for a monochromatic wave, we all know the Stokes limit for a sharp wave crest. And actually, there's an instability just before that happens at Ka close to 0.41. That was a paper by Tanaka from the early 1980s. But for random waves with the spectrum, how do you actually define the steepness? And so there's 2 schools. So first, Klaus Hasselmann came up with an idea, okay, we're just going to use some average steepness defined from the entire spectrum. So that was really brave. That was in 1973, or sorry, 74. And then Owen Phillips was looking at waves and currents, like, yeah, not today because we have no waves, no currents, but usually here we have waves and currents. And was looking at that and said, well, it can be a linear thing. Waves start to break a lot more when they go against the current and the steepness goes up. And so we started to think, okay, we should do something different, and then we should do something which is nonlinear as central spectrum. And he made some arguments for that, looking at working with a non-dimensional spectrum, which is called now the saturation spectrum. And in the end, it's really Owen Phillips, so this nice guy here, which unfortunately passed away about 10 years ago. I think really won the argument. So if you follow Phillips, the wave dissipation should be product of a breaking probability of the waves and the dissipation rate per unit breaking crest length. And so for that, Phillips introduced what's called the lambda function, which is essentially the density. It's a very funny number, but the density of crest length. So you count the length of the crest per unit surface of the ocean. And actually, it also has some kind of spectral version of that. It's also per unit phase speed in wave number space, or in the two axes. Anyway, so essentially you're counting the number of crests. That's something you can measure with some radar, with some video. It's nice. It's very good for experimental people. And then the idea is that, okay, the dissipation rate for a given wave should always be more or less the same thing. And people in the lab have found that the dissipation rate to scale, that's Duncan at the University of Maryland, that's the dissipation rate to scale with some B coefficient times the phase speed to the power of 5. Now, there's a lot of struggle in getting this B coefficient because some people say, oh, no, actually, it's not quite a constant, it has to be a spectral shape. And so, yeah, so you can look at all the papers by Romero and Delville and others. So it's still a lot of work going on this because we still have a hard time getting some numbers on how much dissipation there is in one breaking wave. But at least we have some framework for defining how that is. Still, when you do this, you have the issues. Okay, but these, if you look at short waves, they're riding on top of long waves, and so there's many things happening to them. There was an interesting paper proposed by Longet-Higgins, 1968, I think, in which he proposed there was a Mather effect. You can get some funny resonance that the long waves should gain energy from the short wave because they're modulating the short waves. But then Klaus Hasselmann pointed to Longet-Higgins that actually he made a mistake because he forgot to consider the potential energy of the short waves riding on the top of the long waves. So there's still some effect, but it only happens if you have a modulation of the wind stress along the wind profile. And actually, that effect with the wind stress modulation can be pretty good. Then there was some observation. For example, Banner looked at some stereo imagery data and showed that if you have a breaking wave, behind the breaking waves, usually the surface is pretty smooth. And so we introduced some parameterization for these short waves, which are wiped out by the long breaking waves. Essentially, if you have the lambda estimation, then you can use this lambda to see how much waves are passing by the short waves and compute just get this energy out. Then there's also some effect that the short waves are steeper on the crest and less steep on the trough, and so it's a never-ending story, and we're trying to get all these effects in the model. So that's the the way it should be, and just to tell you the way it should not be and still used today at the TMWF. This is the WAM cycle 3, cycle 4. Essentially, it's based on the Hasselmann idea of this mean steepness, which was just an easy thing to compute. So essentially, he said, okay, I'm going to compute some mean wave numbers at this spectrum, multiply by some wave number to the power r. Okay. And if I just have 1 over r here, the power, this number is non-dimensional. And actually, if you really want to make a mean steepness, like a mean squared slope, r should be equal to 2. That's the only reasonable number you should use. Now, for some crazy reasons, in the model, they ended up using r equal minus 0.5, which actually is giving a lot of weight to the long wave and not so much to the short wave. So that was used in WAM cycle 3 and 4. And they finally got back to r equals 0.5, but still not r equal 2 in a recent update in the WAM code. And the result of this, and then that's the WAM cycle 4 version of the dissipation term. So you have this mean steepness here, KR HS to the power 4. that's a very big term here. So if you change this mean steepness a little bit, this term goes crazy. And then you have this k over kr and k squared over kr squared. And so my image here, okay, is imagine you're defining the mean steepness. You put this point over which the heater torta will hinge. And so if you put more weight on more energy, you're going to weight the k to the power something on the high frequency. That's going to be low frequencies, right? But now if you have some swell on top of the WinC, that's going to change the mean steepness and move the kr to low frequencies, and then the buoy will feel like an elephant. And the buoy becomes an elephant. This is what happens. Have it here, the buoy like an elephant. Where is it? It's here. So that's a very simple calculation. You take the ECMWF model. You start from 2 meter swell with a period of 20 seconds, which can happen. And if you do that, the WinC has a very hard time growing. You know, it takes 2-3 hours until the WinC restarts to grow, compared to the same situation without any swell. Okay, and really that's really not realistic. I mean, some people have said that, okay, if you have some swell that you can modulate the WinC, you get more wave breaking, but that's really an artifact of the very bad parameterization in which the swell has a very big impact on the results. And so it used to be really bad with the 2005 version of the WAM code from ECMWF. You see that you were going back to the asymptote only very, very slowly. You know, even after 10 hours, there was still maybe a half a meter difference. The new version is a bit better. That's between the green and the blue, but still you can see the difference even after 10 hours. It's converging very slowly back to what the WinC should be. Okay, so that's what should not be used in the model. So already mean steepness is very bad. All right. So all these different source term parameterization, you would think that they should give more or less the same results, and actually they've been tuned to reproduce more or less the expected model behavior. So again, people were expecting the input and information balance, but then if you actually run this very simple uniform ocean model, one point, you assume there's infinite ocean. Here the wind is 10 meters per second, is constant. You start from 0 wave height. In this case, there is no swell. The green line is the ECMWF parameterization, and the red line is my 2010 version of ST4. And you can see that the growth initially is pretty different, and oh, actually no, it's the other way around. Yes. Yeah. So the green is my, and the red is ECMWF. Sorry. So ECMWF actually grows to this nice free developed sea. So people believe that if you blow the wind forever on the ocean, at some point you reach a saturation level. Actually, we don't have any data for long enough at high winds because there's never an infinite fetch and infinite duration. So, you know, maybe that exists, maybe not. And actually, my model doesn't quite do that. It actually keeps growing, but slowly, and it's keeps growing like that. And the reason for this difference is a very important term in the ocean, which people haven't talked much about, is swell dissipation. And swell dissipation is really the most sensitive term in the wave forecast globally. And the basic reasoning for defining the ST4 parameterization was actually to start by first estimating how much swell is dissipating and then adjust everything else. And since we have done that in 2009, then everybody else say, okay, yes, we need to also tune the swell dissipation. Well, the only people that done before was actually Hendrik Coleman in ST2. He found that, yeah, it was getting too strong swells if you didn't do something special for swell dissipation. So swell dissipation. So it's a very strong impact on large scales, but because swells travel thousands of kilometers, it is locally a very small effect. We're talking about milliwatts of energy loss per meter squared. So it's actually impossible to measure locally, or almost. That was actually the PhD thesis of Ian Young. He was trying to measure that in the lab, and he found there was a JFM paper, 82, I think, and he found that basically the measurement was within the error bar around 0. You couldn't tell if there was actually swell dissipation. We know there is swell dissipation because if you actually make waves in a tank in a laboratory, and you stand at the end of the laboratory, the tank, you will feel wind generated by the waves. And there's a very nice paper about wave-generated wind. Forgot the author, 1960 something. I'll get it back in my head. But yeah, so people that do lab experiments, they know that waves make wind. And there's actually good evidence in situ of wind-generated waves and the effect of swell on the atmospheric boundary layer. So there should be some loss of energy to the swell. Now, how you measure this? The most famous experiment for measuring that was an expedition led by Walter Munk in the 1960s, and that led to a very nice paper called Swell Across the Pacific. It was published in 1963. And so Walter Munk went to some nice islands in the tropical Pacific. They deployed pressure gauges from New Zealand in the south all the way to Alaska. And the problem with that experiment is that all their measurement systems were pressure gauges with a cable going to shore. So they had to be close to an island. And they were looking at how much of the energy was lost during the propagation. At that time, they were believing that the strong currents in the tropics would do some funny things to the waves. And it turned out to be actually not so important. But the problem is, so they essentially found that the energy was more or less conserved. There was some dissipation for waves longer than 13 seconds, but their estimation is problematic because of the islands, and the islands actually take away some energy from the swell. So we didn't have the chance to go to the tropical Pacific, but so we used CT capture radar data, and we looked at storms and swell measurements across satellite tracks. And so that, if you imagine you have a storm here at the red circle in North Pacific, the waves travel essentially along great circle routes on a straight line on the tier, or there's some deviation with the current, but that's not very big. And all these tracks here are passes of Envisat, and if you are lucky, the satellite will pass and follow the same wave group at the group velocity every day after the next day, and we can have repeat passes over the same wave group as the waves travel. So it doesn't happen very often, but we have 10 years of data. And so already at that time, we had quite a few data. And so we managed to find 20 cases, and this is one of them, in which you see the swell wave height measured by the satellite. So these are different symbols as a function of the distance from the storm. And that's in thousands of kilometers. So we go from 2,000 kilometers all the way to 10,000 kilometers as the waves reach the coast of Peru. And the important thing here is that on this path, there is no island. So you don't have to account for the fact that island will block part of the energy. The only thing you have to fight is this error bar, is SAR measurement. The SAR is a very nice instrument, but somehow people that were working on SAR processing, they got tired after the 1990s. Klaus Hasselmann worked a lot on this. Then Bertrand Chaperon found this nice, quite a linear algorithm to derive the wave spectrum from the SAR. And then they just gave it to the space agency and then went to do something else. And so the problem is, one of the problems that the way it's implemented at ESA, there's supposed to be a wind direction effect on the modulation of the SAR roughness and transforming that to wave heights. And so at some point you should put in some wind direction in the processing. And for some lazy reason, they never do that. They just say, okay, the wind direction is 45 degrees. And so as a result of that, you have some biases in the estimates. And so if somebody of you wants to work on this, actually maybe Bertrand will finally do something about it. I'm just trying to kick his ass, but it's taking some time. But there's still some big error bars, and some of these errors are systematic, and we know about them, and they could be corrected. But right now we have to use this. So typically we have only a 20% error on wave height, and I think we can do much better than that. So once you take into account these error bars, you can actually fit some attenuation coefficients from this point to that point. If there is no dissipation, you expect to follow the blue curve. Essentially, would be just dispersion effect. The wavefront expands, and so that's why the wave height goes down, and actually goes up again after 10,000 kilometers, because on the sphere, the wavefront actually comes back together again. Okay. Of course, there's continents in the way. If without any continents, it should actually go up again on the antipode from the storm. All right, so in that case, we found that actually the factor 4 dissipation factor for reduction in wave height, which was supposedly due to dissipation. And what we found is for small wave height, so actually it's pretty big swells. You know, you imagine 4 meters, which is already 4,000 kilometers from the storm. So at the storm must have been like, you know, more than 10 meters probably. For much smaller swells, the dissipation is apparently much less and almost zero. And so it seems that dissipation rates is actually nonlinear, and there may be a threshold beyond which it goes from linear to some nonlinear thing. And so we made some assumption that maybe what was happening was that the friction between the air and the ocean was causing the swell to dissipate. And so there's still a lot of debate about that. Some other people say it's due to the fact that waves make turbulence in the water. I really prefer that theory, but and we started doing some TFD verification of that, but it's only with a smooth surface and without any wind. And so we expect, you know, in this RT boundary layer, the wind should probably play some role. So we don't know. And so this was the first parameterization that was actually corrected with a paper by Leclerc at 2013. So that's the swell stuff. So now we have all the ingredients for the model. So we need some wind input. And the way when I started working on this, actually the Janssen input was giving reasonable magnitude of the wind input, and I will tell you how actually I get this estimated the magnitude. Then you need to have typically some wave age dependence on the stress and the wave growth, that between some growth coefficient and then some correction for wave age that gives you something like at least 2 coefficients you can tune. Then okay, you can play with a nonlinear fraction from the EIA. Then the breaking term, there's a different way to define it, but one nice way I think is what we did with Jean-François Philippot as part of his thesis. As a result of that, you have at least 2 coefficients to tune. One is essentially the B coefficient, and another one which we played with is actually how you take into account the fact that not all the waves in the same direction, and how different waves in different direction lead to breaking. And so this is why we ended up with 2 coefficients to adjust. But then the swell dissipation is nonlinear, so you have this threshold, you have some dissipation coefficient, so that gives you at least 3 parameters for the swell dissipation. Probably there's some effect of long waves on short waves, both on the input and the dissipation, so 2 more parameters, and so you end up with at least 9 coefficients to adjust. Because all these things are known more or less empirically. And so that requires at least 9 different parameters or situations in which you have to measure the waves and adjust your model. So the standard, what people used to do is just look at the wave height in such limited growth conditions. But that's not very good because, again, between ST2, Tolman and Chalikov, and ST3, which is Janssen et al., there is a factor 3 difference in the input, and still you get the same growth curve, more or less. One interesting thing you can add in is the mean direction as a function of frequency in Planck flat condition. I will show you that. Then you have to put in some swell decay measurements, looking at directional spreading, and also look at the shape of the swell fields. So there's many things you can use actually to control better the wave model. And oh yeah, forgetting that there's also mean square slopes. I'm going to skip this. Yeah, okay, this is an example of using the mean square slope to tune the model. So I showed this curve, I think, already yesterday. So this is a distribution of the mean square slope is essentially the frequency to the power of 4, and there's a d squared coming into this. Yeah, like that's d squared times the spectrum, and you integrate that. That gives you the 4th moment of the spectrum. And the mean square slope is the 4th moment divided by some constant. And the nice property is that this mean square slope is very close to 1 divided by the backscatter of radar altimeters. So altimeter is a very good estimator of the mean square slope, and it is a global distribution of this mean square slope as a function of wind speed and wave height. This is what is given by the ST4 parameterization from ZWF, which is really not the right shape compared to that one. This is a first attempt at trying to get this. And you see the cloud of points crossing. At some point, the blue is on top of the orange, and which is not like here. And the difference between this and that is the introduction of a sheltering term, which is essentially a reduction of the wind input at the higher frequencies, and we put that in because otherwise we could never get a balance between the input and dissipation for the short waves. Still, when we do this, when we do this, yes, when we do this and we look at the shape of the spectrum, yes. One term is a sheltering, the other term is a cumulative effect, which is the fact, the way we do it in ST4 is that the short waves are wiped out by the large breaking wave. So that's what the cumulative term is doing. And if you look at the spectrum multiplied by the f to the power 5, so if the spectrum is decreasing as f to the power -5, and you multiply by f to the power 5, it could be flat at high frequencies, and a value for the level of this tail at high frequency is given by Phillips from his Nights of 1958. Actually, people have revised that higher later, but you expect the spectrum to behave like that at high frequencies. Without any cumulative effect, there's really no way you can get the balance. So essentially, you have not enough dissipation. So we introduce the cumulative to bring the tail down, but still it's too high. So now we're talking about 0.6 hertz. That's short waves, but so that's including the cumulative effect. And this, yeah. So we go from here to there, and then we go back up when we introduce the sheltering term. But it's worse for the shape of the spectrum tail, but it is better for the mean-square slope distribution. And this is where we are today. So we're trying to bring this down and still have this cloud of points behaving like that. And now it's not exactly at high wind speeds. There's some problems. So at high frequency, we have a big problem that we don't get the balance right, and all the parameterization have the same problem. ST6 is even worse; it goes higher, and ST3 actually they impose a tail to go to like f-5, otherwise it goes lower. And you would think, okay, why should I worry about the tail? There is really no energy in the tail. Well, the thing is that the tail, if you think in physical terms, that will carry a lot of the stress, and so the U star will depend on the tail, and so the growth of the dominant waves will depend on what's happening in the tail. So there is a connection between the tail and the dominant waves through the growth term. So this is one reason why we care about this tail shape. Also, I happen to be working in a laboratory that does a lot of remote sensing. And so when you look at the echo from the sea surface using altimeters, radars, radiometers, the shape of the short waves is very important. So we really want to get a good description of the short waves also for remote sensing applications. Yes? Yeah, that would be the same. It's actually when I call this here HMF, I just run their quantization in my model standalone, but we've done some reruns with I think the output in mean-square slope, so we could actually check that. I'm looking at Lucia because she's working with a one model. Yeah. And actually, I have some slides. Yes, I actually have the slides from Jean Bidlot. He sent it to me. I can send you, but it shows the same thing. It goes like that. And Jean was comparing that to buoy data, computing a pseudo mean-square slope, take the acceleration spectrum from the buoy omega squared times the spectrum, integrate that, and you get some numbers. And you know, the plot from Jean looks exactly the same. So there's a lot of things that you can use in this type of data to try to see, okay, what makes a reasonable balance or not. So one is the shape of this distribution, then you have what the tail is doing, and so we've done some adjustment after this one to get the tail. Actually, we ended up putting back the f-5 tail. I hate that, but because it's not physical, it's not a source term, but at some point you need to have the tail, which is not going too high, otherwise it's not good for some applications. This is also just to illustrate you what you can do with swell shape. Okay, this plot is a little funny, but it shows the maximum wave height due to a swell from this storm here. So the waves go away, and so you see at some point it's red and it goes to green and purple. This is from the observation from the SAR. This is using the NL1 nonlinear interaction term with ST4, and this one is using the NL3 without any tuning with ST4. And you can see very directly that if you change the nonlinear interactions, you will have the energy will go much more in all the same direction, like this, and you have almost no energy going in this part of this storm. So this is to show that there's some potential for using the shape of the swells derived from SAR data to also control the balance of the source terms in the storms, because depending on how much energy you put on the sides, you get a different pattern of wave going away from the storm. NL3 is a multiple DIA, and so there's many coefficients to tune, and then actually Hendrik has this nice toolbox for tuning it. If you want to play with that, you can do it. I gave up on it. Okay, so this is where we are. Breaking, dissipation. Just a few words about slanting fetch. That's a case I was looking at during my PhD. This is off the US East Coast. This is Duck, North Carolina. This is Outer Banks. So the Chesapeake Bay is up here. And this is a wind field on November 9, 1999. And the wind is blowing from the east, from the coast, but it's not perpendicular to the coast. So it has an angle. And the angle from the wind to the coast is about 20 to 30 degrees. And if you look at the model results at a point close to the coast, you will get, okay, this peak is coming from the Atlantic, it's a swell. It's a punch. And this funny banana-shaped thing is a wind sea. And you can see that at high frequencies, 0.5 hertz, the wind sea is going pretty much in the wind direction or around the wind direction. But then you have this blob of wind sea, which is actually propagating along the coast. And this is a slanting fetch wind sea. So here actually you can have two peaks in the wind sea. One wind sea is blowing along the coast and the other wind sea is going downwind. And this is because the fetch in the alongshore direction is very large compared to the fetch in the downwind direction. And so the wind is transferring energy at oblique directions, also with nonlinear interactions, right? And even if this transfer is locally weak, it adds up to a pretty big amount of energy along the fetch. And as a result of that, you have a change in direction as a function of frequency. And you can use this to say something about the source imbalance. So this is a, oh, that's an old plot, okay, whatever. So this solid line is a measurement of mean frequency as a function of direction. This symbols here, the triangles going to the right, are the Tourmalin-Charlikov parameterization. And this one is WAM cycle 3. And the point I want to make here is that we're looking at the peak of the spectrum where most of the energy is, and between the two, you have 30 degrees difference. Everything is the same, we just change parameterization. And what this means is that if source terms are weaker, you have a less of a steering by the wind. So essentially, it's all the propagation effect and the building up of the energy along the coast, which is making this energy. Whereas if the source terms are locally stronger, that will pull back the spectrum towards the wind direction. So the magnitude of this direction at central frequency is actually telling you the strength of the source terms. And it is based on this that I just said, okay, well, the Tourmalin-Charlikov is too weak, and let's get rid of that. Then I ended up with a problem that the swell has an impact on ST4, and so I say, okay, on ST3, and so I say, okay, I need to make my own, so that's why I started ST4. All right, so I showed you that before, cumulative, blah, blah, blah. And so in the end, these are typical monthly reports from ECMWF. This is a scatter index for all the forecasting centers. For the North Sea buoys is ECMWF in red, UK Met Office, Météo France. This is our model here, the Danish Met Office, and I don't know what MTN is. But typically, you know, it's possible to get better forecasts than ECMWF, especially in the North Sea, just because the parameterization are better. But we're using the same winds. So the analysis, of course, they assimilate some data, so it's not too far, but you look at the forecast range, is it's usually better with our model. And that's not the case everywhere, okay? That's all the global buoys. So in this case, the analysis at ECMWF, the red curve is better than the other ones, but finally we get better after 4 days, okay? That's the significant wave height, and that's for the peak period. So in that case, it's Météo France who's giving the best forecast. Météo France is actually using our parameterization inside of the WAM code and using ECMWF winds. And on top of that, assimilating altimeter data. That's probably the best combination you can do today. And that's North Pacific. So here, yeah, And US, yeah, but on US East Coast, EastNRF is really much better, and that's really our short fetch bias. So when NCEP changed their forecasting system 3 years ago from ST2 to ST4, the people on the Pacific were super happy because they were getting much better forecasts. But the people on the East Coast were not happy at all, the forecasters, because the forecast actually was worse than before with ST2. So this is why we're working on improving the short fetch behavior and also working on the U star, because the wave age effect on U star can also improve that possibly. But it's still work in progress. That's in the Mediterranean. Yeah, the error here. So it's almost a joke. You know, they do all these statistics, but for some reason in the TMDF model, they always add up the tail of the spectrum to compute the TMO2, and they compare that to buoy data in which the tail is not added. So if you don't make a consistent comparison, this is why you get this very big difference. But even the scatter index in our case is less than their scatter index. But yes, we have. This is to show you that if you don't compute the parameters on the same frequency range, you can make big mistakes and you get this factor 2 difference in the error. That's the mean period TMO2 in the Mediterranean. Okay, I think that's the end. I'm getting there. So, yeah, so actually there's a lot of heuristic adjustments to the source term parameterization, because for random waves, the wind wave growth and the braking can be whatever you like. And there's few measurements of the details of how the dissipation and input is broken up into different frequencies and also directions. So when you actually work with the parameterization, you really have to look at a lot of different types of data and do that comparison to make sure that you don't get crazy results sometimes, like the effect of swell in the WAM code. And on regional at global scale, you know, the most important thing is really the swell dissipation. All right, so you have to make careful you get the right tuning for this. The wind stress parameterization can have some big impacts on the short fetch behavior. There can be some spurious interactions of the wind C and the swell in the model, and that is gone away since we've moved to this Phillips idea of the dissipation compared to the Hasselmann way of having a mean steepness. And as I said, hopefully we can use the mean square slope and the wind stress together to get a better shape for the short waves. Oh, no, it's not finished. Can I have some shallow water stuff? Okay. Any question about the deep water things? No. Okay, let's see what I have about shallow water. Bottom friction, braking, infragravity waves. Whoa. Okay, let's just do a little bit of bottom friction. So basically, yeah, the bottom friction is important only if you have waves with a significant orbital velocity. So significant is, I don't know, at least a few centimeters per second at the bottom. And of course, that depends a lot on the wavelength of the waves. So in the Atlantic, where the typical wavelength or the typical period is around 8 seconds, the effect of the bottom friction would be important, say, in 50 meter water depths. In the Mediterranean, where the waves are much shorter, it's going to be more like 20 meter water depths. So it really depends on what wavelength you have, and so the rule is that it depends on the velocities at the top of the wave boundary layer over the bottom. You expect that the dissipation should be affected by bottom roughness, and the bottom roughness can actually change due to, well, biology. There's a lot of things living on the bottom, but also the fact that when you have a movable bed like sand or silt, this bottom influenced by waves can make ripples, and that's another important source of change in roughness. So a lot of people are still using the very funny John Swap parameterization, which is supposedly derived from the experiment John Swap. Actually, if you read the report from Klaus Hasselmann from 1973, it's really funny because he had a theory before for quadratic bottom friction. The theory didn't work at all. So he said, okay, maybe there's some important tidal current, so I can linearize the tidal current and get some linear stuff instead of being quadratic. And then when he does that, he had a coefficient of dissipation was varying by 2 orders of magnitude, which means that it's useless. But still, people use it a lot because they, I don't know, they liked it. All right, so you can also instead go to more physical-based things that you actually look at bottom roughness and changing bottom roughness. And for that, well, but you need to know the bottom size and grain size and type. So this is a map of the grain sizes on the French coast, the That's the median diameter going from, well, 10 centimeters is actually rock, and that's pebbles, 1 centimeter, pebbles a few centimeters, and gravel, and then fine sand, 0.1 millimeter, going all the way to silt. Now, if you look at the impact that this has in the model, this is a difference in wave height, the average difference over 1 month between the so-called Jones-Swap parameterization and the Shorwax parameterization, which uses this effect of the bottom roughness. So you can typically have mean differences of more than half a meter. And this region here around L'Île-Dieu has this nice rocky outcrop, and this is where we actually are lucky to have 1 buoy. So we actually could tune this roughness to get exactly the right height at the buoy, and this is what we did. So, so the bottom can have a big impact. The bottom type can have a big impact on the friction. It's also true on the US East Coast and the North Sea. I mean, off California, it's pretty deep, pretty fast. So I'm not sure there's much friction going on. Then at some point, the braking will be not just due to white caps in deep water, but also changing what people call the depth-induced braking. So first of all, I hate this dissipation, the difference between the depth-induced braking and the white capping. For me, it's just one braking term. And so you can actually have a continuous parameterization of braking if you look at what would be the proper Misch type limits. And this is a plot of, what is that? Beta, which is maximum wave height, normalized by the tangent of KD as a function of tangent of KD. Okay, so what do we have here? So the solid line here, the solid symbols here is a result from string function theory calculation for the maximum wave height. The crosses here is a parameterization from Roussink. And yes, and the blue here is actually if you convert the wave height to be a linear-like wave height, meaning that if you actually remove the harmonics from the nonlinear waves, and you actually get back to something which behaves a little bit like the Roussink parameterization for the maximum wave height, which is gives you some nice transition from shallow water to deep water, and it's what we use for the thesis work of Jean-François Philippot. So that gives you some way to define a braking probability, which goes from shallow to deep water. So it's a generalization of Thornton and Guza braking probabilities, and then the big question is the dissipation rate. So like the B factor for the deep water. So in shallow water, we know we go to the Bohr type dissipation. So you have a hydraulic jump, and so that gives you dissipation rate in a hydraulic jump, and that people have used that in shallow water, works pretty well. And between this shallow water and the deep water, we have this unknown territory in which we came up with some B parameterization, which seems to be doing a reasonable job. So this is typically two different ways to run it. So in that case, ST4 using the parameterization and the test and the parameters from Jean-François Philippot is giving you the braking of the waves on the beach, and that would be what you get if you use Baches and Janssen dissipation in WaveWatch. So this is a distance from the beach. So the beach is here, and that's offshore, and that's a linear clean beach. Okay, so that's all I had. Yeah, well, what I wanted to say, and I already said before, is that parameterization is not just about the physical processes, because you actually never write the actual physical processes in a model. We are working with spectrums. We have to translate the physical processes in the spectral world, and then you do some approximation, and these approximations have funny side effects if you're not too careful about it. And so it really has to work all the time for all types of spectra. And this is one reason for actually doing this test on the global ocean and making sure that it gives reasonable results. Oops, then I won't show you that. All right, that's it. I'm finished. Questions? Yes. So actually, you have to choose yourself the switch you use. So first of all, you have to choose if you're using the DIA with this configuration of K1, K2, K3, K4. Or you can use a full integral, and in that case you have to put NL2 inside of the switch. And then with NL1, you can change the strength of the coefficient, there's a name is parameter for that, and I think you can put it into lambda and the mu, the shape of these wave numbers. And you can also use multiple DIAs, and that's the NL3, and then you have many coefficients to choose, which is all the geometries of these DIAs. So yeah, that is adjustable by the user. It's defined, so the switch is defined in the switch file, and then all the other things have default values, but then they can be modified by nameless parameters. Yes. How much is it? 20 or 25? I think because if you don't use a feature, it's a switch with something 0. So if you don't have non-interaction, you have to put NL0. If one of them is missing, the compiler will tell you, I cannot compile because you're missing this switch. So it used to be that you start to put some switch, and then you get all these errors. Say, okay, you're missing this, and try again, it's missing that other one, and yeah. So one way to do it. So now we have example of switch files inside of the bin directory. So you can use the switch NRL from the NRL instance, or the switch ntep, or the switch iframer. So I think you have some examples, and then you can do your own. Anything else? Yes.
There is many switch, but in the end, that one we are not using more by
well, HMWF is using ST3, but in their code, which is 1, so it's the same as ST3. Yeah. So HMWF is still using it.
For some parameters, okay, that at this type, okay, you can wait. Can forget about because the new and make a test and you can make a decision.
Is that one way to go? I think technically, actually, ST3 with the latest options is better in some regions. But then that's is that still the default ST4? But then you can also play with like you have 10 parameters you can tune in ST4 to get different things, and then you can get better results here, but it's going to be worse here. And it's a compromise between the swell and the wind sea and the storm and the other. So I mean, we're running stuff globally. We of course have a focus on our coast here, also on the Mediterranean, but mostly on the Atlantic. And so we really want to get almost zero bias and a good score on the French coast. That's the thing. Then we have some other projects that work in the Arctic, in Southern Ocean. So we're also looking at the effect of ice and stuff like that. So we're trying to get everything better everywhere. But I think that still today there's still not a single parameterization which is probably best everywhere. So some specific situation may be better in some other place. There is very specific things, which is all the tropical cyclones. So we tested that in the original paper 2010. It may be that some parameterization work better than tropical cyclones and others. Yeah, so we haven't looked too much yet at tropical cyclones. But of course, they are inside of that. You have tropical cyclones during the year, but not every day. Yes. So this one is a bias, and this one is Arameter normalized. Huh? Yes. It turns a little bit, yes. Yeah. And actually, that was a little bit included in this kind of plot, the bias changing with the season, but that's a global one. But you could do the same. I think there may be some of these plots with different season in Arun Chawla report or yeah. But now you have the tools to do that user comparison, so you can do it yourself. We did that yesterday. Any other questions? Okay, so if not, we're going to talk about dirty, or not dirty, actually run the thing, and the different programs, the structure of the code, and